Hello, morning. Good. Over 4 units. We introduced the idea of electric force. Basically, it's a force that involves electric charges, positive and negative charges. They are usually at a very elementary level, at a very atomic level. It is on protons and electrons. And corresponding to that force, there is an energy which is called the electric potential energy, very similar to the gravitational potential energy. And energy is something we use a lot these days. It is very common. We use electrical devices all the time. But I've mentioned this before also. This is it should be appreciated that 200 years back, when first time this was learned, this was just it was almost a revolution in the sense that every other day they were coming up with new technologies in principle. And at a very simplistic level, that's what we are trying to learn. Even today, they are all applicable, but it is these form the elementary devices that constitute a bigger, more complicated device. So it's important to learn this. So it should be appreciated in that spirit, very much like the mechanics course. We study how the motion of a stone, but very easily, if you master that, you can extend that very easily into more complicated systems, like sending a spacecraft into on another planet. So in that spirit, for the first time now, we change gears in a sense. We switch over to basically making devices or understanding how devices work. So the main idea we have introduced till now, which you want to remember, or if you want to take into the next step, is the idea that electricity stores energy. If you have a configuration of charges, you're basically storing energy. So let me go through that in a few steps. We have the idea of electric potential energy. That's U. And for a point charge, this will be equal to K times Q1, Q2 over R. When I say point charge, it's for spherical symmetry. On the other hand, if you have planar geometry, which is very similar to gravitational field or gravitational energy on the surface of Earth, then you have Q times E and let's call it H, height H that you move. This should be compared with mass, mass times gravity times H, right? Remember potential energy due to gravity is mg H, and potential energy due to electricity, electric potential energy is Q times E times H. That is a pretty much one-to-one analogy in there. The same thing holds for this also. It's just that it cannot be as trivially familiar as this one. If you go away from the surface of Earth, for example, if you're at somewhere where the International Space Station is, the gravitational energy will be given in this form rather than G, which is 9.8 square. That's electric potential energy is very similar to gravitational potential energy, and it has this construction or this form for different geometries. But what we will be more interested is in electric potential. It is again, I want there is no energy, right? So this just remove the word energy from the top, and you can propose called electric potential. And this is V. It is equal to U over Q. So if you have an energy, you talk about energy per unit charge, and that's called the electric potential. This is measured in joules. And this is measured in volt. That's it. Abbreviated unit you construct. This should in principle be, if you put it in SI units, you will put this explicitly in terms of coulomb, and then divided by coulomb, there will be 2 coulombs in the numerator there. So overall, volt is just a vocabulary you build out of the basic units, and you can also say it will be Newton per coulomb times a distance. So that's various forms. You can write it, but we will use the unit volt consistently. This can also be thought of as a concept coming from the electric field. So electric field is force per unit charge. The vector, and you multiply by distance on both sides. The right side gives you an energy, left side gives you the voltage. So that's the basic idea. So that's the main thing we will be talking about, that there is a voltage associated with the concept of energy, or there is a potential difference. So if you think of this as change in energy, so this will be called a potential difference. Electric potential difference or potential difference. Anytime you're plugging in your device in the wall socket, there are 2 terminals there. There is a potential difference you want to achieve between the 2. That's the primary goal, so that you can take pulling energy from that socket. So those 2 points that you see there, they have a potential difference. So the main source of energy is this potential difference, and this Q is what moves from that potential difference, from a higher potential to lower potential, and releases this amount of energy. That could be thought of as, so if you think of gravity, so there is this is a high point, and this is the low point, so this could be ground. And if water is flowing in here, that's water. There is a higher gravitational potential energy, lower gravitational potential energy. When the water falls down, it gains energy. So you have converted gravitational energy into kinetic energy. You want to do the same thing with electricity now. You want to build a potential difference in response to change in potential energy and convert that into movements. Like you want to convert it into mechanical work. So that's the idea here. You have converted gravitational potential energy to mechanical work in the sense you have made water move faster. And similarly, you don't have to be moving water, something you are moving. Typically, it is a motor you are moving, or you will be lighting up a bulb that is energy associated with that. Those are the kind of applications we will look for. So the main idea is, if there is a potential difference and potential energy, or the reverse, you can have a potential energy, you can have a potential difference. And we know already the process where you can confront a potential difference is have charges on one plate and the opposite charges on the other plate, and that creates an electric field. And the simplest way of building or storing energy, we will talk about how much energy is stored in such a configuration today. Positive charges on one plate, somehow you can easiest is to just rub, right? We have noticed that if you rub one material onto the other, if one of them gets charged and or positively charged and the other gets negatively charged. So that's a way of creating an electric field. Once you have created an electric field, the fields are going down. Parallel to that are your equipotential lines. So this is at a higher potential. Higher electrical potential, higher gravitational potential. When you go from higher gravitational potential to lower gravitational potential, you release energy in the form of kinetic energy, and this is lower electric potential. Whenever we do not make it very clear, it is understood that it is talking for a positive charge. A positive charge has a higher potential here. That means it will go from higher potential to lower potential. But negative charge will go in the opposite way, and the negative charge will find a potential. So it will go up. In gravity, we don't see that because masses are always positive. In gravity, everything will fall down. But if there was a negative mass, it would have gone up. But we do not have a negative mass here. We do have negative charges. So positive charges go down or negative charges go up. Either way, you release energy. If the negative charge goes left alone here, it will get attracted in the upward direction, and as it moves, it gains energy in the form of kinetic energy, and you have got mechanical work in the sense that it is now moving. And that's the basic idea. How do you want to convert electric energy into another form of energy? So one of the first things you would ask is, you would like to increase this potential, or even better, you would like to ask, how can we make configurations, geometric configurations of these kind of materials? Always parallel plate is not the most convenient configuration you can build. What kind of configuration we can build, and how can we increase the ability for it to store charge? We would like to rub a material and have charges on it. We'll come up with better ways of charging a material. So we would like to talk about the ability for a configuration to be able to store charge, and that's idea will be called capacitance. And associated device will be called a capacitor. This is the closest you can get to a battery. Like in daily life these days, we use a battery all the time. What does a battery do? It provides voltage, and that's the potential difference it is provided. But after a while, it drains out. What is draining out is the charge. And you would like to store charge in a battery, and how much charge you can store in a battery decides how long that battery will last. And here we are talking about how long will that charge last. Capacitance is not exactly a battery, even though I'm using the analogy of a battery. Battery, the main idea is that you can release the charges very slowly. Like it doesn't happen that you connect the battery to your device and within a second, everything, all the charges are used up. Right? That doesn't happen. It is happening at a very slow rate, and that's convenient because you do not want so much charges to flow all the time. But in a capacitor, unlike that, control is not there so much. And if you were to connect a capacitor to any circuit, it will most probably release the charges probably in less than a second. So it's not very suitable for a battery, but the idea is the same, that it has charge inside it, and it allows us to change at what rate it will release the battery to a certain extent, but not like battery itself, where you can really keep it for days, and unless you use it in a very explicitly shorted manner, it will keep the charge there for a long time. And typically in batteries, we use chemical mechanisms to store the energy. So that is very different from what we are doing here. Here we are using geometry. Mostly the shape of an object will be used to store the energy. So in a certain form, very different, but the concept is the same, that how much charge can you store in a certain configuration. That's one thing. And second, we will talk about, if there is a charge stored, how much energy is stored in the same configuration. So two things: how much charge is stored, that will be a measure of capacitance, will be a measure of that. But what we are eventually interested in is how much energy can be stored in a device. There's one more associated concept: how much energy can be released from a device in a certain amount of time. That is called power. So that is charge. So three concepts we are talking about. So charge, how much charge can you store in a device or a battery? Second is how much energy can you store? And the third is how much energy can be released in a certain amount of time. That's power, energy per unit time. They're all relatively the same, but when it comes to a particular application, you might need one of them over the other. In certain applications, you need a lot of power, and you don't really bother about how much is the total energy. Sometimes it is the total energy that you're worried about. If you're budgeting for a long duration of time, you want to have sufficient energy. It's not necessarily not sufficient that for one day you have a lot of energy and then you don't have much. Then you have charge, and again related in the sense that how much charge you store decides how much energy will be stored. But these are different forms of the same concept we are talking about, but depends on applications where these things will change. Just for you to have a feel for what are we talking about, if you're charging a phone, that requires very less charge. So that's an electronic device that requires very less charge. So that is a less charge. On the other hand, if you are using a flashlight in your phone, like these days, we have again made this pretty well that we do not waste energy so much there. But a flashlight, especially in at a bigger scale, uses a lot of energy, more energy. Or anything that involves heating, air conditioner, heater. So those involve a lot of energy. That's a simple idea we will keep in mind. Whenever there is a heating device, it involves a lot of energy. Electronic devices, anything that is compact in form, there are not much movements involved in that. That's movement in the sense mechanical movement involved in it. That usually consumes very less energy. That's mostly electronic devices. Electric and electronic devices, the difference is that in electric devices, usually there is a mechanical system that is moving, or there is a heating happening. In electronic devices, the stuff that is actually moving is really miniature. They are at atomic level, and the energy you lose in them is relatively significant. That could be used as an intuitive scale in your mind that there is a less what uses less power and what uses or what uses less energy and what uses more energy. So what is the capacitance now? Ability for a device to store charge. And more, if it can store more charge, then you say that its capacitance is larger. If it can store less charge, then you say its capacitance is smaller. And the device itself is a capacitor. The device will be called a capacitor. Another point I should bring up here is that most of what we are doing here is about building devices, and you can build very complicated devices. Think of it like in mathematics, you can do a lot of operations, but all the operations can be at some scale be classified into some elementary operations. Like you have addition and multiplication. If you study addition, multiplication, and division, then you can, using that, almost build everything else. Like you can build a complicated function out of simple operations. So similarly, in electrical devices, we will be talking about 3 elementary devices using which almost everything else can be built. So these are elementary and mostly linear in the sense that they will be proportional, like it is not a square dependent. But that need not be the case in every device, but most of the time that is a great approximation, and that is sufficient to build, go to the next stage. So the 3 devices we will talk about is, first one will be the capacitor. Second one will be the resistor. And the third one will be the inductors. So as we proceed into the course, we will cover these 3 devices. And today we will talk about capacitor. Resistor we will introduce very quickly, but inductor we will not introduce until a later stage, because for that we have to study magnetism. So now we have introduced electricity. Similarly, we have to introduce magnetism. That's the overall picture of a simplistic view of what we are heading to. We want to talk about devices in the sense that we would like to talk about circuits and how when a battery is connected, how can you control things in that. So for that, one of the first devices we are building is something associated with a battery. We said in particular we are talking about capacitance. So again, it is the ability for this device. So if you have 2 parallel plates, how much charge can it store? So let's do an example instead of defining it immediately. So first, let's do an example of the parallel plates. Parallel plates. And let's ask how much, what decides how much charge is stored. So same example, but we want to do this quantitatively. Positive charge and negative charge. And if it is infinitely, if this is of infinite extent, then you talk about charge per unit area. But this time we are talking about real devices. So let's keep it finite. So if it is finite, so it has an area. It has an area associated with it. So now I'm defining the geometry of this plate. So this is a plate. It can be a square plate, and it has a distance. So let's call this H or D. Typically, I think most of the books call it D. It would have been H would have been convenient because then you can compare it with gravity. But D and H is really only understandable. Okay. So the geometry of this device, if you just take two plates, keep it one above the other, then it's decided by what's the area geometry wise talking. That is the area and how far are they from. How much is the distance between them? That's your distance d. There is a charge q you are placing on this. So that's plus q and there is a minus q. And always in a device, we will have the same amount of charge plus or minus separated out. You don't want to have a balance of the charge because if you suddenly have a device in your pocket which is electrically charged, that might not be the most convenient thing. You will get shocks every other time. So it is convenient to have neutral devices. So the main idea would be that these two are of the same amount, so positive and negative. Otherwise, it won't even be stable in the sense if it is not the same. So then there will be an imbalance. So it will try to move out whenever there is a chance. As we said, there is an electric field going from the positive charges to the negative charges, and this time let's particularly ask, what is the electric field? The electric field here is decided by the charge per unit area alone. It is a constant. So electric field is a constant. Let's say this is up. Say that's I choose some x and y. So let's do x. Y is going in. And z is going up. That's just a system of coordinates. So that way the electric field is going down. That's minus z hat or minus k hat, either way, times what is the magnitude of the electric field? That's decided by what's the charge density. It's the formula we derived for sigma over epsilon naught. We are saying that this is a conductor also. So let's see also introduce that idea. So area and let's say this is conductor. It's specifying more precisely what that device configuration is that we are discovering. So we are taking two metallic conductors separated by a distance d. And we have placed a positive charge q on the top and negative charge q at the bottom. And we are asking what is the first? We are asking what is the electric field, and next we will talk about how much charge is stored in there. But sigma usually is not written in terms of charge and area because typically it is infinite of infinite extent. But now it is a finite area, so we can write it as minus z hat times q over epsilon naught times a, where sigma, charge per unit area, charge per unit area is q over a. Right? That's your. So again, two plates. The plates are characterized by charge per unit area and how far they are. And the electric field associated with it is given by this equation. If it was a sphere, remember this would be kq over r square. Instead of r square, now we have the area of the plates coming in. So that's the point. But that decides the force. If I multiply the charge q on it, if I want how much q here will experience the force experienced by the charge, I'll multiply by that. But I'm interested in energy. How much energy can be stored in it? So let me talk about electric potential. Electric potential will be equal to it's like a work done. It is a force times distance. Remember, the work done by a force is work done, force times distance. Here we have electric field, it is per unit charge, so it is electric field times distance, but we want to write it as an integral. So it is minus of the electric field dotted with dl, which path you go along, but it is path independent. So I'll pick 2 points in here. So let's say if you release a negative charge, or let's release it from the top, right? So if we release a positive charge from here, let's think of again water falling, right? If I release a mass here, how much energy is gained at the bottom? That's the idea we want to have. So here, if I release a positive charge, the positive charge doesn't like to be here. It goes down and it gains energy. It starts moving faster. So that how much faster it will move will decide how much energy has been converted from electric into motion. So the change in energy will be decided by the voltage, or how much energy can it gain. So that's the voltage, and that's decided by E dotted with dl. There, dl is going down, so that's here dl. That's the path along which I'm moving. Electric field is also going down, so both are in the same direction. So that's equal to minus of, I can put this is the sign of 0. So that's E dotted with dl. E is a constant, E doesn't change, right? These are equidistant. These lines are equidistant, unlike a sphere where they radiate outward. These are equidistant. Equidistant or equal in density means that electric field is uniform inside the plate. That means it's constant electric field. So E comes out and dl is going down. So what we have chosen our direction to be up. So this gives you E times F. That's the equivalent of G times H. Gravity is to be G times F. The energy per unit mass. So energy per unit mass will be G times F, right? This is gravitational. Right. That's the same idea here. Electric energy per unit charge, which is the electric potential, is simply E times H, or I was talking about D here, right? So let me switch over to D. I use D in here for just for standard. So that's E times D. Potential is very similar to force or the work done. Work done is force times distance. This is the electric field times distance. We are talking about energy per unit charge. So the Q is not playing a role. So we, for our purposes then, we place the magnitude of E in there. So that's Q over epsilon naught A times F. That's what it is. We were asking the question how much charge can be stored in here. So charge Q would be equal to the charge you can store inside or in this configuration on these 2 plates is decided by how much voltage is achieved on it, and it is epsilon naught times A over F. Oh, again, I will go F D. So if I say that I want to have a certain amount of energy as the charge flows from the top to the bottom, that I want to keep fixed. That will be V's being fixed. But then I want to have a lot of charges on it. How will I change it? The only quantity that I can change is the geometry. Right? How can I change the geometry to increase my charge? I'm not going to change by V. So there are 2 possibilities. I can increase my area, or I can decrease my distance between the plates. So charges, the charge stored in this plate will be a lot more if I were to bring this closer and closer. Or if I make this extension large, making it larger makes sense because if you make it larger, there is more room for the charge. That is sort of immediate, but the distance as you get closer, that's a concept that then you can actually increase your charge. That is the third possibility, that you change this constant itself. But then you would say that that's a universal constant. How can you change a universal constant? But that constant is the property of the medium in between. Remember the name of epsilon naught? Epsilon naught was permittivity of vacuum. We didn't dwell into what exactly that epsilon naught means. We just used it as a constant. Here we will actually give it some meaning. It is, for now it is associated with the vacuum. In fact, that is a property called permittivity for any material. It will have to deal with how much polarization it can have, and we will talk more about it. So that is one more feature, that you can actually fill this with a medium. Typically, you don't want to have liquid, but there are capacitors with liquids in it. If you have a liquid, you can have larger capacitance. That is the advantage, but then it is harder to manage. Right? You need to have a better way to seal it. So usually you use simple materials like a paper, for example, is a convenient material that you can put in between two plates. It cannot be conducting, because if it is conducting, then it will short, right? Then it will immediately make the charges move from positive to negative. So you want a non-conducting material, basically an insulating material, and which will increase this epsilon naught. Almost every object has an epsilon naught, or the permittivity larger than vacuum. So any material is better than vacuum in there. And often the materials used is something like paper or mica sheet is the most common that is used. Anything a silicon based, like clay is something that can be used inside a capacitor. So anything that has insulating properties, but at the same time can polarize very easily. And we'll talk about, like, since I introduced this epsilon very nicely. We will come back to that, and that will make more sense. So again, what I want to highlight here is that amount of charge you can store in a capacitor. If I want a fixed voltage or fixed amount of energy coming out of it, is decided by the geometry of the configuration. It is proportional to area. It is inversely proportional to distance. And it is also proportional to the material that you fill it with. So those are the three quantities that it will depend on. And this box quantity you define as the capacitance. So that's going to be your capacitance. So C, the capacitance, is going to be epsilon naught times A over D. Notice it has only geometry in it. And of course, there's a material property in it, but if you're talking about vacuum, then it is just geometry of the configuration, area and the distance between them. And that is what I meant by saying that we will here talk about controlling these electric charges, mostly using geometry, and that makes it more academic in a sense. But in a real application, you don't have that restriction. You can do, you will mostly change the capacitance using the material property. This is much more, it is much more easier to change the capacitance using the material than it is to do it with the geometry. But we will here discuss geometry, but that will give you an idea of what other things capacitance depends. This is, remember, I emphasize that this is only for parallel plates. Parallel. That's a particular geometry. I earlier said that I will confine my discussion mostly to plates and sphere. Here, sometimes on a cylinder, in a homework and in a classroom, but that's all. We won't go too much away from that. But in principle, if you want to explore, you can immediately go into different geometries and very quickly this gets harder, harder to analyze. Parallel plates comes out to be very easy. So let's take this relation here and summarize the idea of a capacitor that we have introduced. Now we're talking about parallel plate capacitor. So Q, the charge you can store in a parallel plate capacitor is V times C, where C is equal, the capacitance is equal to epsilon naught times A over D. This is the relation that will play an important role in the next two lectures. In fact, similar relation. And many of you might have been overwhelmed in the last few weeks for sure. There was a lot of integration. The expressions were unusually more complicated than what you were used to in the earlier semester. Now we take a huge transition. We'll talk about just these kind of variables. Typically, there will be linear. So in that sense, at least the ability to work with formulas should get much more easier. And it does show up. The second midterm comes out to be much easier, and or if not easier, at least less overwhelming. Like easier wise, that is always a relative concept, but it is lot less overwhelming to the students in this course. So expect to work with simpler formulas, not with more complicated integrations. But I will introduce it here and there, but mostly it will be simpler formulas like this. So if this is going to be a primary equation, charge is voltage times capacitance, and if it is a parallel plate capacitor, so this is only true for parallel plates. That's this quantity, and that's all you need to have this picture in mind. What area means, what distance means, distance between the plates, and how you can change is that you can put something inside in there, in a material inside in there. So let's immediately calculate a capacitance. How much charge can it store, or in principle, let's just calculate what a capacitance is. To begin with, maybe I should say unit of C, so unit of capacitance. Right, so that's usually we say dimension of C, right? So dimension of C or unit of C. Let me just say unit, right? So unit of C is unit of epsilon naught. Epsilon naught shows up in Coulomb's law. And it is Coulomb squared, Coulomb squared, not capacitance. That's why I'm writing it in full. So that's Coulomb squared divided by meter squared times Newton. So I'm using the idea that force is equal to 1 over 4 pi epsilon naught times Q squared over R squared. Like epsilon going to the left brings me a Coulomb square over meter square and a Newton, and that is an area which is let me just write it as meter square. So this is meter square, and that is a meter again in the denominator. So that's meter. Let me replace all the everything associated with a Newton. So this is Newton will be kg, meters, again meter per second square. So that's it, Newton. Put this all together, so that's equal to 2 coulomb square. So coulomb square, and there is a meter and a meter in the denominator that cancels the meter square, and there is a meter square left. So this is second square. Divided by kg and kg and meter square. Okay. You don't want to be writing that all the time. You create a new vocabulary. So that's equal to a farad. One of the important persons who worked on this between 1800 to about 1840s, that's when he was most active. Doesn't mean that that's when he lived. He lived between, I think, 1780s to 1850s or 1860s, or so. His name was Faraday. So you shorten it and you say it is Farad. So that's going to be the unit of capacitance. Let's talk about how much capacitance is common for normal simple devices that we talk about, so especially this plate. So let's build a very simplistic capacitor using the parallel plates idea. So you want to create two parallel plates. So that's the capacitance, right? It has an area. A is the area, and that's the distance. And there is an epsilon also. So this is epsilon naught, right? If it is vacuum, that is epsilon naught. You want to build this. If you want more capacitance, then you need to increase your area, reduce the distance, right? Two parallel plates, if you want to keep it very close by, that becomes a pretty big challenge very quickly. But we'll make it simple. We'll just slap one on the other, but then you will say, well, that's not going to keep the charge. So we'll keep a sheet of paper in between. So we need two conductors. Let's take two aluminum foil. Go to the kitchen, get an aluminum foil and keep two of them. And in between, since you don't want to connect the two conductors, so you put a sheet of paper. This is an insulator. So this is a paper. And those two. So this is aluminum. It's different with different colors. So you have two aluminum foils and you have a sheet of paper. Let's decide, and if you want to make a device, you cannot have a huge sheet. So what we'll do is we just want a rudimentary capacitor. We just roll it and make it very tiny. And that is exactly how a capacitor you will make it more sophisticated, but mostly that's how you do it. So you take a huge sheet, keep it, but then you cannot have a 1 meter square capacitor inside your tablet or something. So you want to make it smaller, so you roll it. And how well you can roll it is the technology that matters. But for our purposes, this is just a flat sheet of aluminum. So area is 1 meter square. Let's keep it one significant digit. So 1 meter square. One significant digit calculated because it's not going to be very precise. And the big D between them, distance between them, I said I'm going to keep a sheet of paper. What's the thickness of the paper? The thickness of the paper decides your distance D. What is the thickness of the paper? So you and I don't know. So what you would do is that you get this sheet of 500 sheets of paper, right? So typically that's this thick. I think about 5 centimeters probably. So that's 5 centimeters for 500 sheets, right? Typically there are 500 sheets in there. So that's 500 sheets. So one sheet will be 1 centimeter by 100, right? So it is 10 raised to minus 2 divided by 10 raised to 2 meters. So that's again up to one significant digit. So that's 10 raised to minus 4. So that's 1 into 10 raised to minus 4 meter. Let me write it in micrometers. So that's 100 into 100 micrometers. 100 10 raised to minus 6 meters. So a sheet of paper that you use all the time, that's about 100 micrometers. So that means you can have about 100 bacteria in a line, right? A bacteria is typically about a micrometer. Just telling it in very vague terms so that it gives you an idea of what we are talking about. So just to give you an infusion for the scales. Okay, so distance is about 100 micrometer, but let's write it in 1 into 10 raised to minus 4. Micrometer is for infusion, but then calculated, we have put back the numbers. Okay, so capacitance, that's all. This is all there is, right? So I said our equations will not will get simpler, so that's all we have to do. So epsilon naught A over V, and epsilon naught is 8.85. So there's a cheat in here, right? I said epsilon naught is for vacuum, but now I'm going to use the epsilon naught for a paper. That's not correct. So let me, this is you're not coming across. In the next lecture, we will see it more explicitly. And epsilon for a paper is 3.5, larger, 3.5 times epsilon naught, that is epsilon naught for a vacuum. Right? Remember, vacuum is the perfect insulator you can think of. That's the best insulator. Paper is a good insulator, but it's not as good an insulator as vacuum. And epsilon is a measure of how good an insulator it is. So we have until now said that we will talk about two extremes, either a conductor or an insulator, and that's how we will work throughout the course. But sometimes I said that we might talk about what is the property that decides what an insulator is, and that's epsilon naught. So this is a measure of how good an insulator. So this is a perfect insulator. So if it is 3 instead of 3.5 to 1, then it was better insulator. So let's say this is a paper now. This is paper. This is for paper. So it is 3.5 times why 3.5? It is only one significant digit, so maybe 4. That's 4. 4 times epsilon naught. We're working in one significant digit. So it is 4 times epsilon naught, 8.85. But that's 9 into 10 raised to minus 12. So this is 8 point, just for you guys to remember what I'm writing. So this is 8.85 into 10 raised to minus 12. We have been using 1 over 4 pi epsilon. That comes out to be 10 raised to 9. 9 into 10 raised to 9. But so to one digit, this is just 9. But this is not 9 into 10 raised to 9. This is the denominator of 1. So don't confuse with that. Area is 1. And divided by 10 raised to minus 4. 1 to 10 raised to minus 4. So 9 into 4, 36. 36 is 40. So that's 40 into 10 raised to minus 8. So put two of them in here for the decimal. So this is 0.4 micro. A unit for capacitance we said is farad. So that's farad. Now, of course, a farad, the unit farad. Right? That's a symbol. You say it's farad. So that's how we will work with. Remember the charges, how much charge can you is typically available. We said it is a micrometer and a nano, not micrometer, microcoulomb or nanocoulomb. Nanocoulomb is small amount of charge, microcoulomb is relatively big, and about 10 microcoulomb is a lot of charge. If you go 1 coulomb, that's typically too large. Probably that will be shorting, and you need a lot of equipment to be able to store 1 coulomb of a charge in a stable way. It will immediately create what we see as arcs or lightning and so on. So microcoulombs are what you typically come across, and a capacitor can store a microcoulomb of charge, and it is measured in microfarad. So that's the idea. Again, we have charge. Now we are learning how to store charges, and a capacitor is a device that stores charge. How much charge can it store, and how much voltage, how much energy can it release? That's given by this expression. That's the primary expression, and this is your if you are working with panel plate configuration, that's the geometric expression. We have talked about how much charge is stored, but immediately you ask how much energy is stored in there, right? That's often more important. You would like to energy decides how long a device will run. So you want to talk about how much energy is stored inside a capacitor. Energy stored in a capacitor. So let's try to imagine how you would actually build a capacitor, build in the sense of how you will charge a capacitor, not really having the geometry itself being built. You have a capacitor and you are storing charge in it. So how would you go about doing that? So you have a configuration like this. Let's stick to parallel plates. To begin with, there is no charge on the two plates. So that is charge is 0. So let's say this is the initial. At the end, so there's an intermediate state, and eventually you have a positive charge Q on this plate. So that's plus Q. And that creates a lot of electric field. I made it dense here to emphasize the fact that that's a lot of energy, a lot of electric field, or not a lot of density. If the density of lines is larger, relatively speaking, that means there is more electric or more strength in the electric field line. That means, and we will see that there is more energy there. Somewhere intermediate from here to there. So this is the final state where you have plus Q there and minus Q the bottom. Somewhere intermediate is where the electric field is not full. Yeah, so it is you're doing the process. So how you're going to do this is, how would you do this? There is neutral and plates. So you pluck a positive charge from the bottom plate. You pluck it, that means the bottom one becomes negative, and go and place it in the top one. Right? That's a very mechanical way of saying it, but that's going to require energy. Positive and negative charges like to stay together. So I'm plucking them, so that's a lot of energy I'm going to consume. I'm going to keep it apart and keep it on the top. So that's going to involve energy, and I want to calculate how much energy is involved in doing that process. So you do a little bit. So in the intermediate process, the intermediate step, somewhere I have moved about Q of them here. That's not full charges, a little of them, and there's a minus Q up. So I keep doing small amounts here and there, and I want to reach a final state of plus Q and minus Q. Let's start from here and talk about an infinitesimal quantity, because this is an integration, because every step I do this, and for example, when I go from here, the very first charge I do, it only has to resist my plucking. There is no resistance I experience from the top plate. But somewhere in between, I have to overcome two things. One is I have to, of course, pluck it. But the second is when the positive charges is being pushed there, it doesn't like to be kept there either. So first of all, I have to resist the negative charges here. They don't allow me to pluck that positive charge, and this already existing positive charges do not allow me to place it there either. So I have to compensate for both of them. So let me talk about an infinitesimal statement. So from here to there, so let me put a dq, a small amount. Already there is a plus q and a minus q. So I'm moving this to that side. Pluck dq, a small element dq, and plug it and put it on the other side. And that involves energy, right? Remember, if the voltage is V, then the energy is U is V times Q. So the amount of work I have to do, or the change in energy, dU, to move this from here to there is going to be decided by the already existing charges. So that's Q and dV. Remember, energy per unit charge is the potential. But what is the potential in the intermediate state? V is nothing but Q over C. Like that, C is the geometry dependent quantity. So write it in the opposite order. So this is Q. Since it's a small voltage we're talking about, so this is dQ over C. So the total energy that you will spend to go all the way from 0 to Q is I have to integrate this from 0 to a full charge Q. So I integrate on both sides. And this one I integrate from 0 charge to start with, and I reach a total charge of Q. C is a constant, so this is equal to Q square. So the top limit, so it's Q square over 2. But then I have to do the upper limit and the lower limit. Lower limit doesn't contribute. So it is Q square over 2. And then there is C, which is a spectator there. That just sits there in the integration. Right? It's not as a constant. And the total energy U then is, so U final minus U initial. Let's say U initial is 0. So that's this. So how much energy is stored? The energy stored in a capacitor. So energy stored in a capacitor, taking stored in a capacitor in C is U is equal to how much charge that is, and 3 times C. Right, the capacitance is coming in the denominator. That's not really. It depends on how you want to use it. it's not, it should not be immediately concluded that, oh, C is in the denominator, so more capacitance means it's less energy. That's not the case because Q over C is voltage, right? So I can replace Q with V and C. So this is the same as V times C squared over 2 times C, right? So this is also equal to half C V squared. And if I write it in terms of Q, then the capacitance comes to the denominator. If I write it in terms of V, the capacitance comes in the numerator. So it depends how you want to talk in terms of energy. If you keep charge fixed, then C is in the denominator. But if you keep the voltage fixed, that was the definition of the capacitance, right? Keep the voltage fixed and how much charge can be stored in. So in that sense, when you look at it, more capacitance leads to more energy. So that's half CV squared. We can also write it in both Q and V. C times V is Q. So this is also equal to half Q times V. Right, so different ways of writing it. So let me remove that configuration, that expression. So these are all true expressions and applicable in different times. Like what exactly you're interested in decides which expression you will use in it. This seems to suggest, at least this expression seems to suggest that it is actually the charges that is, or how much charge you place on the plate is deciding the energy. But I want to change that understanding a little bit and emphasize the fact that it is not really the charges, or another view of it is that it is actually the electric field that has energy. How you want to see this is that it's not the charges. Charges are, of course, creating the electric field. In that sense, more charge is necessary. But where exactly is the energy? Is it on the plate? Where exactly it is? It is the electric field. Electric field is what has the energy in it. So let's check that out. So let's talk about how much. So let's calculate let's just rewrite that expression. U. Here it goes. U. So U is equal to, let me say, let me start from the first expression. So that's 1 over Q squared over 2 times C. Remember, if I have a parallel plate capacitor, remember my electric field was Q over epsilon naught times A. It was sigma over epsilon naught, but sigma was, so this is nothing but sigma. So I want to convert this expression into electric field. I want to see how much electric field is in there. What is the measure we can talk about in terms of electric field? So that's sigma over epsilon naught, but wherever I see Q, I can think of electric field. So electric field is something that is proportional to the charge in a parallel plate capacitor. So let me replace this with electric field squared, so that's epsilon naught times area times electric field and square. Putting everything in geometrical quantities and the electric field. This is the electric field strength inside this plate. Q times C. C was epsilon naught times A and over D. So I put it in the numerator D. So everything is either I have electric fields or I have geometry. I have converted the energy stored in a capacitor in terms of geometry and electric field alone. And this is equal to, if you notice, this is, let me write this as one of the areas cancel out. 1 by Q epsilon naught E squared. And there is a geometry left out, that is A times D. So it's A times D. Area times the distance between the plate. Area times the distance between the plates. That's the volume of the plate. Like area times distance. So what we are talking about is U, energy, total energy between the plates, over A times D. That's energy per unit volume. So that's equal to half epsilon naught E squared. Even though we have here emphasized or motivated this as how much varies the energy stored, it's in the electric field. Now you take a leap from here and you say that whenever you see an electric field, wherever you see an electric field, in a per unit volume sense, there is energy stored in that spatial localized region. So whenever you have a charge, it creates an electric field, and that region of space has a certain amount of energy, and that's given by the strength of the electric field in there. And typically it is a vacuum, so it is the vacuum property that comes in. This is what we'll do a very similar concept for magnetic field, and then bring both together, and that's how we will explain light. Light will have both electric field and magnetic field, and there is energy stored in it, and it also has momentum stored in it. So this will play a conceptually important role when we go from here to there, here to the next topic. Thank you.